So let's describe how polar coordinates could be used to describe conic sections. First, we'll give a brief refresher on the major conic sections, and then we'll talk more in depth about how polar coordinates could be used to describe these conic sections. So first, let's talk about why they're even called conic sections. You might be wondering why the concept arises, okay? Why they're called conic in particular. Well, if you have two cones and you attach them as you see here, you could intersect this shape with a plane and you'll get an ellipse with that intersection. We could change the position, for example, and we'll get a different ellipse. Okay, we could also play around with the tilt, and there goes a parabola. And we could get the basic conic sections this way by basically intersecting this plane with this conical structure. So here's a circle. Here we could get an ellipse by tilting. There we could get a parabola that opens to the left. We could get a parabola that opens to the right. A hyperbola, and a point, which is the intersection right where those two cones meet. We could get a single line or a pair of lines. Alright, so let's start with talking about parabola. And what a parabola is, it's the set of points in a plane that are equidistant from a fixed point F, called the focus, and a fixed line called the directrix. Okay, here's the directrix, the fixed line, and here's the focus. And every point on this parabola is equidistant to the focus and the directrix. All right, here we have the vertex at 0, 0. Okay, so this is basically the bottom point of the parabola when it starts switching directions. And here are some equations where we have the directrix at y equals negative p. This is basically what you see over here. And please note that this is not drawn to scale. So you basically get that equation there to describe this parabola. On the other hand, we could have had a parabola that opens to the right. This is described by that equation, but that's not shown over here. So to make that concept clearer about equidistant from the line to the focus, take a look at that. Okay, and so the distance from this point on the parabola, this pxy, it has an equal distance to this line, the directrix, and the focus. Of course, here we take the perpendicular distance from that point to the line. Okay, you can see it forms 90 degrees with the line that's drawn from the point on the parabola to the directrix has 90 degrees when it intersects with the directrix. Okay, and we could move along. No matter where you are, there's an equal distance on each point in that parabola between the focus and the directrix. We could also play around with changing the parameter p so that we can move the directrix. But okay, we're still getting that same basic shape with the equidistant from the focus to the line. Alright, the other major conic section is the ellipse, which is what we see here. Okay, and you could see with the ellipse is the set of points in a plane whose distance from two fixed points called the foci, so each one of these is called focus and the plural is foci, have a constant sum denoted 2a. So any point here has a constant sum between the distances from the focus to that point. It's going to be 2a in this diagram, again not drawn to scale. And for an ellipse that we see over here, with foci at plus or minus c, as we see here, and vertices at plus or minus a. Vertices is basically that farthest extent of the ellipse on the long axis. Okay, so we have the major axis, which is the long axis, and we have the minor axis, which is the shorter one. Okay, and if it's centered at 0, 0, and how we have these constraints, we get this basic form of the ellipse that you see on the left hand side there. Down here it's not drawn, but it's one where instead the major axis runs along y. And to see this constant sum at play here, you could take a look that if you add the blue line and the purple line, they'll always sum, no matter where you're going on this ellipse, they're always sum to that major circle that you see there. Okay, so if you add the blue and purple dotted lines, they'll sum to the major purple line there, that's the radius of that outer circle that's purple. Okay, and finally let's talk about the hyperbola. Okay, and what is the hyperbola? Well, it's the set of points in a plane whose distances from two fixed points, these foci, okay, have a constant difference, either 2a or minus 2a. Okay, and for this hyperbola here to the left, we have this basic equation. Okay, this bottom one here is going to have the hyperbola running along y, opening up along y instead of x. So this is what corresponds to what's drawn there. And again, these are not drawn to scale. And so you can get this basic form of the equation with these asymptotes that you see here. Okay, and that relation between the parameters b, c, and a. And to get an idea of how this constant difference between the foci looks like, well, take a look at that. All right, so you're getting, so you have the dotted lines, that's the distance to the point on the hyperbola. And if you take a difference between them, you'll get this constant difference, is what you're seeing, the purple circle there, okay? The radius of that purple circle. You could see that we could go on both branches of the hyperbola, okay? So that's how hyperbola is. It's a constant difference, whereas the ellipses were a constant sum. Now this theorem here, the eccentricity directrix theorem, suppose L is a line, F a point not on that line, and E is a positive real number. Okay, this is what the eccentricity is. Let C be the set of points P in a plane with the property that the distance from the point P to this point F that's not on the line over the distance from the point P to the line has this constant ratio. Okay, so PL is the perpendicular distance from P to L, and PF is the distance from P to this point F. Okay, it has this constant ratio, which we call the eccentricity. Now, if E, the eccentricity, is 1, C actually turns out to be a parabola. If E is strictly greater than 0 in between and strictly less than 1, C is an ellipse. And if E is strictly greater than 1, then we have a hyperbola. So in one fell swoop, we could basically describe all three of these shapes with this theorem. And again, a picture is worth 1,000 words. So let's take a look at how that works. So we'll have this point F, the focus. Okay. And you could see that that ratio there, the distance between the points on the parabola in F and the directrix is that constant 1. Well, let's play around with the eccentricity. If we go greater than 1, we expect to have a hyperbola. and we do, and now the ratio between that focus and the distance from the line to a point is 1.69. Okay, so the distance from a point on the hyperbola to the focus over the distance from that same point to the line is 1.69 there. Okay, you could increase that distance as well, and you see what's going on. Well, what about if we go less than 1? Okay, so here's 0.3, we get an ellipse. Okay, so that's an ellipse. Then when we hit E equals 1, we get a parabola. And then E greater than 1, we get a hyperbola. You can see that here as well without those lines. Okay, and so basically the eccentricity is that one parameter that could distinguish between parabolas, hyperbolas, and ellipses, depending on that ratio. All right, so let's take a look now at a summary for the properties of ellipses and hyperbolas, and so not parabolas. If the foci are on the x-axis, such as you saw above there, and the major axis would then be characterized by plus or minus a, and the minor axis will be characterized by plus or minus b, just as you see over here. So here the vertex is at minus a, for example, and a for x, and b for y. Okay. On the other hand, you can have the foci on the y-axis, and then you would get this bottom equation if you did that. Okay. And so, and we just discussed this, that if E is strictly less than 1 and strictly greater than 0, then you got an ellipse. If E is strictly greater than 1, it's a hyperbola. Of course, with E equals 1, you got a parabola. And then you get these three equations over here. Okay. So you have this equation there, that equation, and this equation here for an ellipse, and the analog equation for a hyperbola. Okay, that's why I call them 3 when there's actually 4. It's because these are case dependent. It depends on whether you're dealing with an ellipse or a hyperbola. And so these are A through E, and you have 5 parameters and 3 equations. So if you have 2 of the parameters, you could predict the other 3, okay, using these equations over here. Okay, so now let's focus on polar equations and how they could be used to describe conic sections. So let D be strictly greater than 0, basically where the directrix is. Okay, this is going to help tell us where the directrix is. The conic sections with a focus at the origin, so you get one focus at the origin, in eccentricity E, has polar equation this or that if x is either at if the directrix is either at x equals d or x equals negative d. Okay, so you get these two equations depending on if the directrix runs vertically at x equals d or x equals negative d. On the other hand, if we have a conic section with focus at the origin, again in eccentricity E, then if the directrix is at y equals d or y equals negative d, okay, we get these equations. And the major difference there is instead of a cosine, you have a sine. Okay, so which one to use depends on where the directrix is. First, you got to ask, is the directrix running vertically, and so either x equals d or x minus d, or is the directrix running horizontally and is at y equals d or y equals negative d. Okay, in both of these cases, one of the foci is at the origin. Okay, and if it's a parabola, we only get one focus. And of course, again, if E is strictly greater than 0 and strictly less than 1, you have an ellipse. If E equals 1, you got a parabola, and E greater than 1, you got a hyperbola. And the curves are defined over any interval theta of length 2 pi. Okay, so as long as you run 2 pi radians along theta, then you'll complete a cycle for these. And again, a picture is worth 1,000 words here. So, I mean, this is how we'll describe conic sections using theta. And here you could see we have the equation r is equal to ed 1 plus e cosine theta. And that's because our directrix is at x is equal to d. Okay, and we could see as we increase theta there, okay, we're running along this parabola. Okay, we can change the directrix. Okay, and now it's over there, and we could change the eccentricity, and here we should get a hyperbola, but it's kind of difficult to see there unless we play around with the directrix. And again, we could change the angle theta and see how we're running along this hyperbola. Okay, or we could go and get an ellipse, and notice that the origin is at one of the foci there. There is another focus not drawn here. Okay, and again we could vary theta, and as long as we go around 2 pi, then we'll traverse the shape. Okay, so let's take a look at a concrete example. So find the vertices, foci, and directrices of the following conic sections. Okay, and graph this following polar equation. Okay, so we get this polar equation. Now we got to decide which one of these does it fit. Okay, well, we got a cosine theta, so that's going to eliminate these. We're not going to go for that. So it's going to be one of these two. Okay, we see a plus sign there, so we're going to put our equation in the form for a directrix being at x equals positive d. Well, what's getting in the way of being in this form? It's that 2 over there. So what do? We factor out a 2, and we'll get 4 there. 8 divided by 2 is 4. And now we're in that form for the top equation there. Okay, so you can see now we are in that basic form. And the coefficient of that cosine theta, what is it? Well, it's e. And so we get e is equal to 3/2, which is greater than 1. And so we're dealing with a hyperbola with a focus at the origin. Well, what is the numerator there? It's ed. And so we have that ed equals 4. And that implies that d is equal to 4 over e. And if e is equal to 3/2, so we divide 4 by e and get that one directrix there is at d equals 8/3. To find the vertices, we use theta equals 0. That's going to have the radius r at the positive x-axis, and theta equals pi is going to have the radius r at negative x-axis. And since we're dealing with a horizontal ellipse, that is going to give us the vertices. In polar coordinates, we'll get a -8 when we plug in pi in here, and we'll get 8/5 when we plug in 0 in our equation. Okay, so we then convert. These are polar coordinates, so we convert to Cartesian coordinates, and we know how to do that, right? The basic equations: x is equal to r cosine theta, and y is equal to sine theta, r sine theta. So you could convert these, and you'll get these points in Cartesian coordinates. Okay, and this is what we want. And so this is where our vertices are. We just found our vertices. You could see they're over here. Okay, these are the vertices. Well, what about the center? The center is halfway between these two vertices. So what we could do is start at 8/5 and add half the distance between the vertices. Okay, that's what's going on there. And you'll get 24/5, so the center is there, 24/5, 0. What about the foci? Well, one of these is at the origin. How did I know that? Well, these equations assume one of the foci is at the origin. So one is at the origin. Okay, now the goal is to find the second one. Well, first notice, due to symmetry, that the distance from the focus to the vertex should be the same. Okay, so V1 to F1, this is the first vertex, V1 to F1, should have the same distance as V2 to F2. Okay, now the distance from the first focus to V1 is 8/5. And if we impose that condition on the distance between F2 and V2, we'll get 48/5 there, okay, which is just 8 plus 8/5, the distance between the foci to the vertices, okay? And the directrix, well, that's just coming from that standard equation there, okay? We have that x equals d for that form. And we found d to be equal 1/3. And the second one, by symmetry, again, you're going to have an equal distance between the directrices and the center. And so from that symmetry, you'll start with 24/5 at the center and add the distance from 24/5 to 8/3, okay? Which is the distance to one of these directrices. You'll add that from the center to the other directrix, and you'll get 104/5. And we just basically plotted and found all of our relevant points for this problem. So let's do another very quick example. So here we have, we want to find the vertices, foci, and directrices of r is equal to 2, 101 plus sine theta. Well, what form does that fit in? Clearly, we got a plus sign there, okay? And we got a sine theta. And so it's going to fit in that form there. We already got that 1, and so no need to sort of massage that equation to put it in the standard form. We get a parabola because e equals 1. That's the coefficient in front of that sine theta. It's implicit there that you got 1 times sine theta there. So e is 1. ED then is equal to the numerator, which gives us a directrix of 2. Where is that directrix? It's going to be at y is equal to 2. Okay, so it's going to be up here. That's the directrix. Focus is at the origin because that's the assumption of the equations above. And for the vertices, we plug in theta equals pi over 2, which should give us the vertices for this parabola opening downward. And plugging in theta equals pi over 2, we get 1. And converting that to Cartesian coordinates, we get 0, 1. And there goes the relevant parameters there for this equation.